हेलो सर। हेलो, एम आई ऑडिबल?
Hello.
Yes, sir.
Yeah. So, so good morning. So, what's going on?
Sir, I had one request before the class that
Sure.
slides that you are using in the class, can you just upload them in the website, like the slides that you have prepared already? The class notes are uploaded, but those slides are not. At least I cannot find them in the website.
Oh, the slides are not uploaded. Okay. I will upload them.
Recordings and class notes are there, but not the slides.
Okay. I will do that. Okay. Yeah. Thanks for pointing into. Sure, I'll do that. So, any questions about whatever has been done so far? Any doubts? Okay, so no questions. Excellent. So let me. Yeah, some questions. Okay. So where were we in the last class? So let me share my screen. So in the last class, we were looking at these recursive algorithms, and we were looking at merge sort. You can see my screen, right?
Yes, sir.
Yes.
Okay. You're looking at merge sort, and what was the main idea? That you basically you have this whole string, right? X1 to xn. You break up in the middle, and you merge this part separately. You merge this part separately, and then you I mean, you sort this part separately, you sort this part separately, and then you merge this, right? So basically, it's sort left, sort right, and merge left and right. So this was a very simple algorithm, the recursive algorithm. And what was the runtime of this algorithm? Maybe I will ask some people who have not. Bineet Jha, are you there? Okay, you are not there. Devdatta Kanungo, are you there?
Yes, sir.
Yeah, what is the runtime of merge sort?
N log n.
In log n, can you tell me why or how?
I forgot.
Okay, uh, you forgot. I mean, rather you did not read. That's fine. See, I mean, I know that this is an online class and this is a hard to concentrate on this thing. If it was an offline class, it would have been slightly better. But given the current situations and the situation of the amount of space that is ISI has, so having this class offline is not possible. And in an online setting, I can just come, teach, and go, and don't care about who is learning what. I mean, I could do the same thing in the offline setting also. If you don't, guys, if you are not interested in learning it, that's up to you. I mean, I think I'm getting a bit frustrated with these various batches as to what's going on. I mean, it is true that I'll be happy to put in the effort, but if you guys don't put any effort, then I don't see why you guys need to. I need to put in that much effort. See, I don't insist you guys to come to the class. If you are not interested in coming to the class, don't come to the class. I mean, most of you don't even possibly listen to what I say. You just keep yourself muted completely. I mean, I know that this is your first year in ISI and you think that ISI is just not like a normal school where you come, you take some, you come to the class to give attendance and that's it. But sorry, this is not how ISI works. Okay, you are supposed to put in the effort, and if you cannot put in the effort, I mean, I will not be unhappy even once if you say that I don't understand this part. Can you explain me once more? Or when I come and ask you guys, that do you have any questions? If you ask me any number of questions, I will have no problem whatsoever. I'll be happy. But it seems that it's a complete lack of any amount of effort from your end. So Devdutta Kanungo, why are you in the class? Actually, can you just tell me? I'm sure you did not listen a single thing that was told in the last class also, right? Okay, so
Sir.
muted. Yeah.
Sir, I was there.
You are there, that I know. I'm not asking for your attendance. What can we do? Yeah. See, you have come to ISI. We can put in that much, only that much effort as much as you can. You are interested in receiving. If you are not interested in learning something, that's what can I do? Or what can anybody do? Okay, so we had this merge sort, and we had these two things, and as you guys possibly have heard that, so if Tn is the time taken to sort this whole string, then of string of length n or array of length n, then of course since left is of size n by 2, T of n by 2 is the time taken for sorting the left half, and T of n by 2 is the time taken for sorting the right half. And the merge, this takes order n steps. So if I write the recurrence, this becomes T of n equals to 2 times T of n by 2 plus order n. And of course, what is the base case? Now, you can say that, okay, maybe when there's only one element, I don't make any query. So something like this. And with this, if you solve the recurrence, which was also done in the class, and I'm pretty sure most of you have not followed it, but that's fine. You don't seem to have any doubt with that. So we will get that T of n equals to order n log n. Now, a natural question to ask is that, can you get a better upper bound? Can you have a better than n log n upper bound? And the simple thing is that, okay, if you look at this recurrence, this n log n is coming mostly because of its order n part. And a natural thing is that, okay, can we do something better? Why do I need to spend order n over here? What's the problem with doing something more trickier? And if I can reduce this order n to something smaller number, then I will have a better upper bound. So one way is that, see, my job is to split it into two halves, right? And that is where the power is coming up. And then I have to combine them. So if I know that these two halves, the left half is always less than the right half, then I don't need to merge them as such, right? So how can you, so what does it mean by that? So I can say, for example, what happens if I do this following? Okay, split the array, okay, so array A from A1 to AN into two halves. Okay, so some one half and another half, so left half and right half. such that, so maybe let's call this one B, this is C. So this is B1 to Bn by 2, this C1 to Cn by 2, such that Pi, all the elements in the first half is less than or equal to the elements of the second half. Doesn't matter. So any element in the first half is less than or equal to element second half. Now, if I can do that, then I'm done, right? Why? I would go say that, okay, recursively sort the left half, then recursively sort the second half, and that's it. Because I know that all the elements in the first half is less than all the elements in the second half, I can just put them one after another and I will get the whole thing. So my kind of T of n will become something 2 times T of n by 2 plus maybe a constant or something like that. And by doing so, I would be done. Correct. So this is a very natural way of thinking, that if I can somehow avoid this costly merging protocol or merging subroutine, can I do something clever? And this is exactly what happens in the world of quicksort. So what does quicksort does? It takes, okay, so maybe let me just write it in a slightly different way. Let P be the first element, okay, or A1. So maybe I would think of this the input as A1 to AN, okay. Then the protocol is, let P be equals to A1, okay. While I equals to 1 to n, if AI, oh sorry, 2 to n is less than or equal to P, put AI in left, else put AI in right, and then sort left and sort right. So what is happening here? I am just taking the first element and I am splitting up the set, all the A1 to n into 2 parts, left and right, such that all the elements that are less than this P is in the left, less than or equal to in this. All the elements that are more than P are in right. So this is something similar to what has happened here. Like I have managed to split up into 2 parts, left and right. And I am now going to sort the left and then sort the right. And that's it. I would be done. Is this clear?
Sir, the main difference is that instead of dividing the two arbitrarily merged sort, we implement a special P here.
Right. We instead of pivot P. So P is usually stands for pivot.
So is A1 the only choice, or can we choose anything?
Ah, good. I will come to that. Okay, I will come to that very soon. And what is the specialty of A1? Or is there any specialty of A1?
Also, are we using extra two memory, two arrays allocating for left and right, or is that being done in place?
Okay, so the way in which I have written here, I have not told anything here. Okay, So basically, so all I want to do is that I want to kind of write this thing into this way, right? So this is all the elements that are less than p, then I have a p over here, and then all the elements that are more than p, right? Actually, you can do, and this will be the left, and this will be the right, right? Actually, this thing can be, all of this stuff that I've written here can be done in place. So I would so you guys should go back and try to see how you can do it in place. It's very simple.
Okay, sir.
So you can do this whole thing in place. You don't have to create a new array called left, or create a new array called right. Okay. So it can be done in place, and then you so left will be the everything before the p, and right is everything after the p. Okay. Any other questions? Okay. So what is the so is there anybody who is not convinced that this is going to give you a correct answer? So what is the runtime of this algorithm?
N square in worst case.
Oh, why?
If it's sorted in opposite direction, descending
Why?
order kind of.
Why? I have given you an ask. You are giving you are telling me something which is possibly true.
Yeah, because
But
if we are
yeah.
It's linear.
func-
This algorithm is linear.
Sorry.
It's linear.
It's linear. Okay. Somebody saying linear. Why linear?
Are you asking like the whole algorithm or just the
Oh,
while
so you are
loop
saying
part?
this. You are saying this while loop is linear, is it?
Yes.
Yes, the whole while loop is linear. Okay, fine. This I can now understand that. Why? Because you can just go over
So-
this whole thing. Yeah.
So if the while loop is linear, then when we think of worst case scenario, we can say this array is sorted in reverse order. So A1 will be the maximum. Then sort left will be constant and sort right will be O of n minus 1.
Okay.
it will be kind of summation of 1 to n.
Yes.
Okay. So
Hello, sir.
you are right. Yeah. Go ahead.
Sir, if we assume that there are k elements less than p, then we can write Tn equals to Tk plus Tn minus k plus order of n.
That's true. We can write that.
But
So
how
if-
are we going to, we don't know k, how are we going to solve it?
Yes, we don't know how to solve it, right? So this is Tk plus Tn minus k plus order of n, right? Now the problem is that if the n is equals to something like k by n by 2, magically it becomes n by 2. Then this is exactly same as the merge sort kind of stuff, right? In
Yes,
that
sir.
case, I would get T of n equals to order n log n. But is there any guarantee that this k equals to n by 2? No, right? K is just saying that this is the number of elements less than p, and p is some a1. Now, maybe that there's nothing less than p. So k can be. So actually, this will be, if you are a bit more careful, actually speaking, this will be p minus 1 or something like that. Because so left plus right is n minus 1. Right? Because this is an n set thing. P is one element, and everything less than or equal to p on the left will be n, and another one will be right. So if k equals to 0, which means that there is no element that is less than or equal to less than p. In this case, this is just n minus 1, right? So in that case, all I can say is that t of n equals to t of n minus 1 plus order n. And if you solve this part, this you will get to be equal to t of order n square. Now, see, this is the upper bound, right? So in some sense, from here, I can always say that, see, you can prove, okay, so this is something I'm giving you as an exercise, prove that from this you can say that t of n equals to order n square. Prove it. Okay, this is an exercise. But that doesn't mean that df, I mean, maybe there's some other calculation through which you can say that, oh, see, if I do this calculation nicely and all, it will become
Sir.
much smaller.
Hello.
Yeah.
Okay, so for
Hello.
this last statement, shouldn't it be less than equals to order n square? Because like order n square occurs in the particular case for k equals to 1. It's
Okay,
not
so
generally
order n
equals.
square,
Okay, yes, yes,
statement of
yes, I understand. Okay.
order n square is already a less than or equal to thing.
Yes, yes, sorry, I missed that. Yeah.
Okay, so order n square doesn't say that it is tight. It is not theta n square.
Yes, yes. Okay.
So Tn is order n square, means the runtime of this quicksort is less than n squared in some sense, constant times n squared. But question is that can it be much lower? And I think your friends were giving us examples where T of n would be equal to n squared. So your friend, so there exist examples. This is, if you guys have understood what your friends were saying, well and good, else you find it for yourselves, where T of n would be what is a omega n squared. So that means this runtime of this algorithm, at least in the worst case, because it's a there exists, so that means there exists a particular input instance. So that means in the worst case setting, okay, and I should be very careful here, it is just the worst case. Quicksort is or theta n square. Okay, so worst case time complexity quicksort is theta n squared. Is this clear?
Yes, sir.
Yes, sir.
Okay, excellent. So we have not made any progress. In fact, if at all, we have gone down backward, right? I mean, we had merge sort, which was order n log n, and now we have given you an algorithm that seems to be more intuitive to some level, but it is order n squared. Not good at all. But one thing that you should kind of realize is that there's one advantage that we had, which was there already in other papers, but this is an in-place sorting. I mean, I told you that you go and check it out, but you can take my word that this is an in-place sorting. You don't have to create a new array, something that you had to do in the case of merge sort. Okay, so this is some good thing, but you say that, okay, what is the useful of in-place sorting? I mean, we had selection sort or bubble sort or whatever sort. They were in-place sorting also, and they were doing it in also order n squared. So what is the advantage of quicksort? Now let's try to see a question that one of your friends asked. What is this P? Can this P, do the P has to be A1? Does it have to be the first element? What do you guys think? Does the correctness of this algorithm depends on the first element being set as P?
No, sir.
No, sir.
No, right? I could have chosen P to be any element, right? So I can choose P to be AI, whatever that I is, some element. Okay. And then you would argue that how does it help?
Sir, we can exchange it with the first element and then repeat the procedure.
We can do that. We can put in the, but basically the pivot, what we are doing as a pivot is basically I can pick any element, right? That's the main idea. You can swap it to the first element and repeat the process. That's the, yeah, you're right. But what do you think? Will it help? Look at this algorithm. So this was the thing. And if I can get K to be something like n by 2, I am in good shape. What is this? Yes, I know that there exists some weird picking up of, in the worst case, picking up of an element where this K will become 0. But what happens if I pick an arbitrary K, a random K, I, so P equals to a random AI? Then what happens? Say it is something very simple like this.
It will be
Hey.
like if partition will be in the middle half, then our complexity can improve.
Can improve some level.
Like
Yeah.
n by 2 to 3 and the rest part 3 and by 2.
Right, good. So what your friend is saying is that, see, once I have something like this, if K can be even something as something bad, but something like say n by 3. So if K is say more than n by 3, I mean say between n by 3 and say K is between say n by 4 and n by 2. Okay, I can assume that, or K is n by 4 and 3n by 4. Then T of n equals to Tk plus Tn minus k minus 1 plus order n basically becomes something like T of n by 4 plus T of 3n by 4 plus order n. Now, this is not exactly true, but what you can prove is that if this is the case, and if I have this one, then I would have T of n equals to order n log n. So if magically I can somehow hit a K which is somewhere in the middle, not too far in the initial part, not too much in the back, somehow I magically pick this thing. Okay, then I can prove this. Okay, nice. Okay. Now, is it possible? Is this too much of a wishful thinking? Now,
Probability half.
yeah. So it is something similar to if you have a school in which there are various students at different heights, right? If you randomly pick up a student, what happens? Okay, that student might be the shortest in the class, might be the highest in the class. So you have this, if I kind of think of them as a sorted thing, okay? So if I have a sorted order, okay, n of them are there. If I pick up a random thing, now, okay, I can pick up this one. Yes, I can. This is the shortest. I can pick up this one. That is also possible. So that is short. That is the longest. But intuitively, I should be hitting somewhere in the middle, right? That's what the chance of me hitting is there. Now, to be more formal, if I look at, say, x n by 4 and x 3n by 4, how many kids students are there in this group?
N by 2.
50%.
N by 2. How many students are there in this rest of the group?
N by 2.
Together is n by 2. So if I pick up a random one, probability of hitting one student from here is same as probability of one student from outside, right? So probability that a random pick is between xn by 4 and x3n by 4 is half. Okay. So what it means is that if I pick a random I, so instead of this pivot I, if I just say that pick p equals to a random AI, or meaning I pick a random I. So if I want to make it a bit more concerned, pick a random I between, so I should erase this part completely. Random I between 1 and n, p is set as AI. Then with probability half, okay, with probability half, I am really off, no doubt, right? But with probability half, I am very close to this middle, and a probability half, therefore, my algorithm, okay, it is not true exactly, because probability half, I can guarantee that the first step that I take will split up into two halves equal, right? The first step that I take, the first partition I take, will be split into two almost equal halves. So we can hope for it. Okay. So this is something that I should say that you possibly most of you have not seen this kind of an algorithm. So this algorithm is what is called as a randomized algorithm. So here the idea is that the input is not random. Okay. I am picking up a random I between 1 and n. Okay. Then I am setting P to be AI, and I'm doing this whole thing. Okay. And in that case, what you have to do is that what you have to compute is what is the expected runtime of the algorithm. So we kind of see that, okay, we expect that the first split will be kind of not too skewed. But can I finish this whole process in a nice way? Is it possible that I will be doing a good job of overall, I will take less time? Okay. Yeah. So let me give you two ways of thinking about it. Okay. One of them is a very simple technique using basically whatever we have discussed so far. Okay. So basically the thing is that, see, again, the first time I pick a point, with probability half, I split up this whole thing into two halves of more or less equal size, right? So that's the main idea of not more or less equal size, but okay, of not very skewed. Let's put it this way. Now this is only happens with probability half. So what does it mean? It means that if I say I pick up a point, okay, I, and I split. Now, if this whole thing splits into two halves, well and good, of more or less equal size, great. But what happens if it doesn't? Then what happens? Okay, so in that case, in the first slot, maybe I have produced, I have the string, I have produced a P over here very close to this side, and this is a much bigger size. Okay, not good for us. In the next round, I will take another P. That another P, one of them will be splitting this part, one of them will be splitting this part. But given that so what is the probability that I will split this half into two halves of equal size or more or less equal size? Again, half, right? But I have already assumed that with probability half, I could have split up into equal size. So that means after every second round, I can expect that the splitting will be done in such a way that all the blocks will be smaller size, will become constant fraction shorter. So in some sense, yes, I don't go down from n to n by 2 in one step. In unexpected 2 step, I should be going down from n to n by 4 kind of stuff, or n by 3. And that is good enough for us. So that is the intuitive way of seeing it. What is the non-intuitive way of proving it? Okay, so let's see again. So let T of n be the expected runtime of quicksort on an array of length n. So what is T of n? It is expected. Remember, it's an expected. How do you calculate it? Do you guys remember the expected definition?
Some summation over probability of a certain event multiplied by the output.
Probability of a certain event happening multiplying by the whatever happens with that thing,
Exactly.
right?
Yeah.
Okay, so what all events are there? What all the randomness are there?
N factorial different permutations.
No. What is the probability over here?
Sir, can you just repeat the last 2-3 lines? Like after you wrote TN, I was having some audio problem.
Okay, so I'm saying that, okay, so this is Tn. So I want to write Tn, the formula Tn. Okay, so I'm saying that, okay, so Tn is an expected runtime, right?
Yes.
So what is the definition of expected? So your friend told that expected means summation of the probability of an event happening, summation over all the events, probability of an event happening times the random variable associated with that event. Right? So here, what is the probability over?
Sir, probability over means we have to start from like consider all the values like linear time to order of n square. All the expect times we have to cover.
Here the probability is
why?
over all possible values of k that ranges from 1 to n. So,
Right. So probability over meaning which place have I used randomness? Hello.
Yes, sir. I had one question. Like
Yeah.
I cannot formally define it, but however, wouldn't the data that we have to sort, if that is in some sense skewed, wouldn't that affect the runtime or the n by 2 assumption?
No, it will not. No, it will not. It will not. Think about it.
Okay.
It all I mean, this A1 to AN can be 1 to n, can be 1000 to n,000. How does it matter? It's all about dependence between combining two elements, right?
Yes.
It's all about the order of this A1 to AN. That's it. What the values are, how, nothing, it doesn't matter. Okay, we will see it. Okay, formally we'll see it. What's going on here. Okay. But again, so whenever we deal with a randomized algorithm, it's very important to understand where the randomness is coming. And in this algorithm, the randomness is coming only here. Yes, the final output might be either log n or can be n, or can go up to even n squared or something like that. Fine. But the randomness is only over here when picking up the pivot. Right? So there are n different possibilities of the events, namely I can be 1, I can be 2, I can be 3, till I can be n. Okay. So if I equals to 1, now what is the probability that I equals to 1?
1 by n.
1 over
1
n.
by n. And in that case, what do I get? What is the time complexity?
N
N
square.
square.
Don't jump again. What I'm writing, what is T of n to n by n? So the
In that
first
case,
thing
time
doesn't
complexity
determine the thing.
ON.
Sorry?
Tn minus
In that
k
case, it will be linear.
Tn plus Tn.
T. Sorry,
N
I got
minus 1.
lost.
Tn minus 1.
Okay, Tn minus 1. See, actually, it's not Tn minus 1. So let me let's not do it
Big
in this
O of n.
order. Okay, so then maybe
Plus
that's what
big O of n.
You
We
guys
have to somehow
hold on.
define k corresponding to the first element, right?
Yes.
Because that has no
Hold on,
particular
hold on,
value.
hold on. Let us without loss of generality, let us say that the ordering is x1 less than x2 less than x3 till maybe just to make our life simple, let's make them all strictly equal. Okay, now what is the probability that p equals to xi? Okay, so these are the ordered version of A1 to AN. Okay, I've just written the ordered. I don't know the order, of course. That is what I want to find. But I can still mathematically ask, right? Mathematically say that, so let's this be the ordering of A1 to AN. So which is x1 to xi. Now, what is the probability that x is equals to xi? Okay, what is it? So p equals to xi.
This is 1 by n.
Hello.
1 by n.
1 by n.
This is 1 by n, because see, the way in which we have picked up is I have picked up an I randomly between 1 to n. I don't know what is it. And I've told that, okay, p equals to ai. Now that ai, I have no idea what is it, right? It can be this one, 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 it can be anywhere, right? So this xi might be in the first element, maybe. Okay, maybe the ai equals to the first element. In that probability, p equals to a, xi equals to I equals to 1, which is 1 by n. Right. So for any, so this is for all I. Is this clear?
Yes, sir.
Okay, at least somebody told yes. For the rest of you, it is not clear, I assume, right?
Sir, this
Clear.
in this part we're just checking the probability of how to choose the random element, right? For choosing the p.
Yes, I'm asking you what is the probability p is the ith smallest element.
Okay.
not ith element in terms of the in the array, but ith smallest element.
Yes, sir.
Yeah, and p is a random element, so it can be any of them, any one of them, right?
Yes.
So yeah. So now let's see the expected runtime. So one of them is the p can be equals to x1. If p equals to x1, this happens with probability 1 by n, right? And in that case, what is the runtime? It is p equals to x1. So everything else will form in one side, and there will be nothing over here, right? So this will be t0 plus tn minus 1. So this corresponds to p equals to x1. Okay. Now there is also this p equals to x2. What is that?
So
This also
that will
happens with probability 1 by n, right? Right?
Yes, sir.
Hello.
Yes, sir.
yes, sir.
I mean, you don't have to just say yes, sir, or no. If you have any doubt, you can tell me what is it, okay? Because this is something that I'm sure you guys are not used to seeing this kind of calculation. See, I'm just calculating the expected time complexity. Expected time complexity is I split it up over the various events, probability of the event happening, and in that case, what is the time that I've taken? Note that I am not putting here order n square. Why am I not putting here order n square? Can somebody tell me why am I not putting here order n square?
Sir, why would you like
It
it is the
will be
delay like p equals to x1 means we have divided the two subproblems into no element on one side and all the larger elements in the n minus 1 element. So that is the two subproblems we have to deal with. So we would sum over them and then
Exactly.
get the result. It's,
Yeah, so this is just a one step. Okay, this is not saying that, oh, if I make this mistake, then that is taking me order n squared time. No, this is just one step. This says that I will be splitting up into a skewed way. That's it. Okay, so this is not immediately order n squared, or neither is something else suddenly order n log n or something. So if I write it this way, I can write, and at the end I will get t of n minus 1 plus t of 0. So in other words, what will we get? T of n equals to 1 by n into, now you can just add it up. See, you can have this t0 to n minus 1 and t0 to tn minus 1. So it will be 2 times summation ti I equals to 0 to n minus 1. Okay. Okay, of course, this is not the final thing. Then there is the order n over here, which is the
wouldn't
time
the
taken.
sum be up to n by 2 minus 1 because we have like superimpose the two sides, right? Having 2 by n. Like
No,
first and last element we have combined to get. Okay, no, yes, yes.
no. This is this thing is t0
Yes.
to tn minus 1. This is t0 to tn minus 1, and that's why 2. Okay, and then there's the order n, which is for that is required irrespective of whatever is being done, which is for splitting up into this left and right side. Okay, so this is the randomized query complexity, sorry, randomized time complexity of the quicksort algorithm. Okay, it's not it's a recurrence. Now I would ask you guys to go back and prove, okay, and this is something that you can prove again for simple induction, that t of n equals to, can you guess what will happen? So this will give you T of n equals to order n log n. Okay. So yes, this query complex, this quick sort algorithm basically has the worst case runtime of n square, but somehow the randomized quick sort algorithm has order n log n. Now there is another concept here that I would like to say. It's called the expected runtime. So not expected, average case runtime. So what is an average case runtime? So let me go back to this quick sort definition. Now, if I had not done all of this randomly choosing I and all, and if I had stuck to P equals to A1 itself, then what would have happened? If I stuck to P equals to A1 itself, then I could not have told anything about the randomized, so there's no randomization that's happening, right? But then one would say that, okay, look at this input, A1 to AN. Again, we are only concerned about what is the order of these inputs, right? A1 to AN. It doesn't matter which is big, which is small, or how big, how small, or anything. So there are how many ways this input can be given to me? This input can be given to me in n factorial ways, right? And I can ask the same thing, that if so in a particular input, so you realize that if I had just P equals to A1, that's it. If I use a different color. If instead of all of this I had P equals to A1, then this runtime will change depending on how these inputs are given. If they are in a, say, as somebody was pointing or referred, the input was given in the reverse sorted order or something like that, then it would be very costly. Okay, if it was not given in the reverse sorted order, but some other way, it could have been lower, could come up quicker, right? So question is, what is the average time complexity taken? Yes, for in particular input, for a particular ordering of A1 to N, maybe it takes order n square. Maybe for another ordering, it takes order n log n, and so on and so forth. Right? So I leave it to here also, I leave it to you guys to go back and think a little bit. What's happening here? Okay. Go and prove that this average case runtime or average case runtime is actually nothing but the expected runtime in our setting. Expected runtime of the randomized query complexity, randomized quick sort. Go and argue for yourself that the average case runtime will be equal to the expected runtime of the randomized quick sort. The main idea, I can kind of give you a very small hint, is that when you are randomly picking, when you are talking about randomly ordering this A1 to AN, and you are choosing always the P to be first element, then what is the probability in some sense of P to be the, so P equals to A1, okay? And I am going to order them P1 to A1 to N in a random way. not random way. I will be permuting it in all possible ways, right? So for what fraction of the inputs will P be pointing to the ith smallest element?
Assuming that all permutations are equally likely, it would be
Yes.
1 by n factorial.
Exactly.
Sorry, 1 by n, 1 by
factorial?
n. For 1
1 by n
for-
because n minus 1 factorial of them
Yes,
would have
all-
pi at the same
Right.
position, and n factorial is the total. So 1 by n.
Right.
1
Right?
by n.
And that is exactly what we have used in our calculation, right?
Sir, can you please explain this once more, because I didn't get that, the average
Okay.
case thing.
Okay. So you understand what the average case is?
Yes, I understand the definition, but the calculation you explained just
Okay,
now, I
okay,
didn't
okay.
get
Yeah,
it.
yeah. Okay. So think of this P equals to A1, right? And I have A1 to AN. I'm talking about all possible permutations of A1 to AN. Right? So my question is that what fraction of the permutation will the A1 be pointing to the ith smallest element? The A1 can be the smallest element, say, okay? So among all the possible permutations of A1 to AN, for what fraction will A1 be the smallest element? Yeah. Hello.
Yes, sir.
Yeah. How much will it be?
n minus 1 factorial by n factorial. Yes.
N over 1, n minus 1 factorial by n
N
factorial,
minus
right?
1 factorial divided by n factorial.
Okay. Which is how much?
1 by n.
1 by n, right? So I have to compute the runtime for all possible different permutations of A1 to AN, right? And then I have to take the average of them. But another way is that I'm asking for what fraction of them will P be pointing out to be the smallest element? What fraction of them, portion of all the permutations, will P be pointing out to the ith smallest element? And you can see that for all of them, the fraction will be 1 by n. So that means with fraction for 1 by n fraction of them, P is pointing out to the ith smallest element. And this is how I calculate, right? So with 1 by n fraction of them, P points to the smallest element. In that case, the time complexity is this. Okay, and for similarly for all of them. So the calculation will be exactly same as what is being done here. Is this clear? Who was having doubts?
Yes, sir. Yes, sir. Now I got it.
Now you got it, right? Okay.
Yes.
Okay, good. So let's see. So I have left a few things for you guys to go back and check in your at home. So let me see, where are we in the world of sorting? So we started with insertion sort, and this one was order n squared, and we kind of, I hope that you guys remember that we had talked about a data structure that we might be useful, that is required to do what? Find and insert in say small, order n. Is that all that we could find, right? Can you do it even better? Okay. Then there were other things that were called selection sort and bubble sort, something that we have not gone over details. It is there in the slides. but they are all both order n square algorithms, and they were not very illuminating, let's put it this way. Then we moved on to coming up to merge sort. Now merge sort was a recursive algorithm, and this gave us order n log n. This is in the worst case. So the worst case was n log n. But it had a problem. What was it? This space complexity was an extra additional order n. We needed an extra additional order n. Then we moved to quicksort. And the quicksort also in the worst case was really bad, sadly enough. But the space complexity improved. So what was the space complexity for all the above things? I will leave you guys to think about the space complexity. Okay, actually speaking, for all of them, if you want, you can do with space complexity, no extra space complexity. But then we had this randomized quicksort, and this gives us the randomized time complexity became n log n. And because of it being this quicksort only, so the space complexity was order 1. There was no extra cost. So this is where we are now. We have a merge sort, which is n log n, that is the great. We have a space complexity of order n, unfortunately, and we can move on to we can have quicksort, which is randomized query complexity, or what you can call as average case time complexity of n log n. But the space complexity is really good. So the question now is there a sorting algorithm? Okay, I have two questions. Is there a sorting algorithm of worst case runtime of order n log n and a space complexity of order 1? Is it possible? Is it there? And more importantly, I want that, can we have sorting algorithms better than n log n? Is it possible? So these are the two questions
sir.
that we would like to answer. Yeah.
Order n, but will be extra space.
Order n by extra space. Okay, how?
I'm forgetting the name of the algorithm, but it's there.
See, that's the problem. If you
No, sir.
memorize things, such thing will happen.
No, sir. There is no way of doing it better than n log n if we are doing comparative sorts. Non-comparative sorts can improve it. So I think he's talking about counting sort, which is a non-comparative sort. But they are very special and very useful in a very special situation, not in general.
Yeah, we'll see. Yeah. Yeah, so these things are pretty, yeah, in some sense, as your second friend kind of pointed out, I mean, yeah, you cannot have a special class of, so all these kind of sorting algorithms will not be able to do better than n log n. But okay, so we have these two questions. So what's the time that we have today? Okay, so let me try to talk about this particular part. Okay. Now, before I talk about it, I want to see what is it that we were asking? What is a sorting algorithm? And this is something I think we need to go back and ask. What is a sorting algorithm? What is it supposed to do? So sorting algorithm can take A1 to AN and it outputs a sorted array, right? And outputs AI1 to AIN such that they are sorted. Now, important thing is that whether these AIs are integers or they are real numbers or they are rational numbers, does it matter? Actually, it doesn't, because all we care about is that we are asking, we use this particular question, okay, is a number less than or equal to b? This is a question that we keep on asking. We keep on comparing this kind of stuff. Comparing, take two elements A and B and say, is A is less than or equal to B or B less than or equal to A? And so these are called comparisons. So this is something similar to what one of your friend had asked in the beginning of this quick sort thing, that does it matter whether these algorithms are skewed? Actually, it doesn't matter, because we cared about only this kind of questions, right? Is A less than or equal to B or not? Whether A is much smaller than B or A is much bigger than B, who cares? This was not our job, right? We wanted to understand that how is A and B compared. So in that sense, I can give this A1 to AN can be anything, can be real numbers, can be complex numbers. In fact, for people who are a bit more from the mathematics, this can be anything that is of a total order. I can give it from anything. Total ordering is all that is required. And done, right? Okay, so if this kind of, but one might think that there might be other things. Maybe there are sorting algorithms only specifically done to understand sorting of integers or sorting of some kind of some 2-digit decimal representation, something like that, right? Okay, so those are slightly different, but whatever we have done, we have only compared two elements. So these are called comparison sorts. Okay, so all of them that we have seen till now are comparison sorts. Now, what is the best part of comparison sorts? That we start from somewhere and we ask, is A less than or equal to B? I can get three answers. A is equals to B, A is less than or B, A is bigger than B, right? And depending on the answers that I get, I make some other queries, right? So C is less than equal to C, B or not. Again, I will have three answers. Does this picture ring a bell?
Yes, sir. It's another
Yes,
decision
sir.
tree.
It's a
Computational
tree, right? Good. And at the end, what do I have? The leaves. What is a leaf? What is a leaf? Leaf is the output. What does an algorithm output?
The sorted array.
The sorted array, right? The sorting, right? The sorted. Right? So here I have been given A1 to AN, and here you are outputting the sorted arrays, right? So so it doesn't matter what I am giving you, right? If I give you, I can give you A1 to AN, and whatever the sorting it will give you the correct sorting array, right? So how many leaves has to be there?
N factorial.
Number of leaves has to be n factorial, because there are n factorial different possible ways of sorting one, right? I mean, there is only
So we
unique
can
way of sorting it, but I could have given you.
Different argument, right?
Sorry.
We can use a different argument, right? Like we can start from a sorted array and we can reverse every operation. Then it
Right,
should be
you
able
can
to
do that.
create all.
Yes,
Yeah,
yes, yes.
that
You
would.
can do that also. Either of them. Okay, this is the same kind of stuff that you talk about. Yeah. So number of leaves is more than n factorial. Every node has degree how much?
Three. Non-leaf node is 3.
Yes, has degree less than equal to.
Less than equal to
I mean, they can have 0 kind of stuff also, right? So therefore, height which is equals to the worst case runtime, right? This is at least log of n factorial base 3, which I am going to just tell it to you, but you can go and check it out. This is n log. Okay, this is something that you can go and just verify for yourself. Okay, so this is verified. So this means that there any comparison based algorithm for sorting has to have runtime at least n log n in the worst case. Okay, any questions about this? Hello.
Yes, sir.
Any questions? Okay, I guess you have understood everything.
We could have taken omega n square also.
Which one? Here? Here?
Yes, sir.
No.
Yes, sir.
No. So this quantity is not omega n square. Okay, so omega meaning it is bigger than n log n. Okay, so this quantity as n goes to infinity is bigger than n log n, or a constant times n log n. But this quantity is not bigger than a constant times n square. Okay, so in other words, this is actually small o of n squared. You can go and prove it. Okay, so basically what you can try to do is that log of n factorial base 3 divided by n squared. Limit n
Okay,
tends
okay,
to
got it.
infinity, you will find it to be going to 0. Okay. In fact, you can say do even further. I mean, you can have n log n and then put anything else, say log n. This will also go to 0. Okay. So anything go to 0. So this quantity is actually omega n square log. Okay. Now I have just done it for the worst case, and I leave it to you with another question. What about the average case? A comparison based with average case small o of n log n. Okay, question. Okay, you guys go back and think about it. Okay, so this is where we are now. So we understand that n log n cannot be bit in the case of worst case at least, and space complexity question, is that okay? So right now we are somewhere here. Can we do something here? Yeah. Okay. So can we get, so next question is, can we have a sorting algorithm of this kind? So I think I will stop here today. I will start again on next class, in which we will move forward and see how can we, if this question is actually true or not. And yeah, we'll take it from there. Any questions? Okay, so if not, let me stop the class
Sir,
today. Yeah,
sir,
go ahead.
sir,
Yeah.
can you explain the height part again?
Okay, so if I have a tree, okay, if I have a tree, so you know what a tree is, right? Hello.
Yes, sir. Yes, sir.
If I have a tree where every node has degree at most 3, okay, then if I have a height h, then how many nodes are here at the end?
Sir, n factorial.
No, no, no.
3 to the
Forget n
power
factor.
3 to the
Yes.
power n.
3 to the power?
N minus 1.
No, this is h. Why n minus 1?
Sorry, 3 to the power h.
Okay, 3 to the power h minus 1 or 3 to the power h. Okay,
Yes,
right?
h minus.
And I know that the number of leaves from another calculation has to be bigger than n factorial, right? So 3 to the power h must be bigger than n minus 1 factorial.
Yes, sir. Yes, sir. I got it.
H must be bigger than log of n minus 1 factorial.
Yes, sir. Got it.
This is exactly the same argument that was done for the case of binaries, for the case of searching. Okay, we had a lower bound argument for searching also before. Okay, is it clear now?
Yes, sir. Got it.
So, sir, can we discuss or ask questions regarding the problem set for practice, or would that be limited to tutorials?
No, that will be done in the tutorial.
Okay, sir.
Okay, so fine. Okay, so any other questions? Okay, so if not, I will stop the class now. Okay, thank you.